In the previous lecture, we learned about the forces that contribute to the development of the resting membrane potential. And just to quickly recap, the resting membrane potential is established by the sodium-potassium pump, which is always running, and leak channels, open channels for potassium, offset by a very small amount of leak channels for sodium. In a neuron, the resting membrane potential is -70. And as long as the only forces contributing to the membrane potential are the open leak channels and the sodium-potassium pump, that membrane potential will stay at -70. And that is what we refer to as the resting or the default state. But there are many gated ion channels that are also embedded in the neuron. And if you start opening up those, now you're going to get additional ion flow that's going to change the membrane potential. So in this lecture, we're basically just going to look at what happens if I have a gated sodium channel. I don't really care at the moment what the stimulus is, just it's a sodium channel and it's gated, and I open it, what's going to happen? How is the membrane potential going to change? What if it's a potassium gated channel? What if it's a chloride gated channel? What if it's a calcium gated channel? And so what we're going to do is try to predict which way the ions will move, either in or out of the cell, based on their concentration gradient, and then what is that going to do to the movement of charge and therefore the membrane potential. So just real quick, let me remind you that I have ECF and ICF, and I've left up the millimolar concentrations of the various ions just so that you can recall where an ion is more concentrated, in the extracellular fluid or the intracellular fluid. Again, for my class, you are expected to memorize this by the first exam. Let us say that I have a gated channel for sodium. And so you can see that here. Right now it's closed. But let's say I open it. Which way is sodium going to want to move? Will sodium want to move this way in the cell or this way out of the cell? And the answer is into the cell. So sodium is going to want to move into the cell because it is so much more concentrated outside of the cell, so it wants to diffuse into the cell. So let's say that sodium starts coming into the cell. Well, that's bringing positive charge into the cell. What is that going to do to the membrane potential? Well, the membrane potential was at -70, but now additional positive charge is starting to come in, and so that's going to take that membrane potential and it's going to start making it more positive. So you would see that change on a graph like so. We would start with -70, which is our baseline. Let us say that this triangle represents the event where we open up a gated sodium channel. Sodium is going to come into the cell, so we expect that that sodium is going to create a more positive environment. Now let's say that I close the sodium channel at this point. So let's actually just go ahead and write that in. What do you think is going to happen to the membrane potential now? It looks like it's somewhere around -40 or -30. Is it going to stay there? Is it going to keep going up? Is it going to drop? What's it going to do? Well, once the gated ion channel is closed, then that gated ion channel no longer represents a path for sodium to come into the cell. So no further sodium is coming into the cell. So it's definitely not continuing its climb upwards. But the sodium-potassium pump is going to start kicking that extra sodium out, and then the leak channels are going to reach their equilibrium again. So we actually expect that the membrane potential will drift back down towards its default state of -70 millivolts. So by opening and closing specific gated channels, I can create deviations from the resting starting point of -70. I can create a deflection up, or I can even create a deflection down. So let's consider another example. Instead of a gated sodium channel, I'm going to use a gated chloride channel, which I typically use green as my color for chloride. So if I open up that gated chloride channel, which I will do here, which way does chloride want to move? Into the cell or out of the cell? It wants to move in the cell based on its concentration gradient. So chloride is going to move into the cell. Chloride is negatively charged. So what that's going to do is bring more negative charge into the cell. Well, that's actually going to make my intracellular fluid, which is already pretty negative, even more negative. And so what would I expect on my graph if I open a chloride gated channel? Well, let's take a look. Let's let this be the event that I open a chloride gated channel. And because more negative charge is coming into the cell actually moves down into negative territory until I close that chloride gated channel. So once I close that chloride gated channel, what do you think is going to happen to the membrane potential? Is it going to stay super negative? Is it going to continue to dive, or is it going to start coming back up? Well, once again, once I've closed all my gated channels, the only forces left at work are going to be the sodium-potassium pump, which is always at work, and the leak channels. And collectively, those always find their balance back at minus 70 millivolts. So we're going to see something like this. Okay, when we see these deflections going up or down, we have names for those. So if you are at some status point, like the resting membrane potential, and then your membrane potential starts going up, we call that depolarization. So this highlighted section of the graph represents depolarization. So where did that term come from, to depolarize? The word polarization means separate, opposite. For instance, right now you might say politics is highly polarized. It means people are on very opposite ends of the political spectrum and there's not a lot of middle ground. So to depolarize is to bring things closer together. Now, in this case, we're not talking about politics, we're talking about charge. So at minus 70, the intracellular fluid is more negative than the extracellular fluid, and it's quite different. As the intracellular fluid becomes more positive, the charge difference is less. They get closer together in terms of net charge. So that's where that term depolarization comes from. So any deflection on this type of a graph that goes up is going to be depolarization. Now, what happens when you've depolarized, you stop depolarizing, and then you go right back down? What do we call that? We call that repolarization. The green highlighted section is repolarization. So what about the change in the graph when chloride channels are involved, where the membrane potential is already pretty polarized and then it becomes even more polarized? Do we call that repolarization? No. We call that hyperpolarization. So hyperpolarization I've highlighted in red. So what happens when you close that gated chloride channel? What do we call the area in blue? Interestingly enough, we don't actually have a name for it. It's not really repolarization because you're already super polarized, so to repolarize doesn't sound correct. It's also not really depolarization because you're going from a hyper state back to a normal state. So instead of having a word to describe the area that's in blue, we simply used words to describe what's happening. We say the membrane potential drifts back to the resting state, or drifts back to the resting membrane potential. So it's important to understand that opening and closing gated ion channels can create deflections in our membrane potential. And we have words to describe those deflections. If they go up, that's depolarization. If they go down, that's hyperpolarization. This is an image from the book that shows exactly what I went through with the terminology. So the important key here is that you're able to predict if the membrane potential will depolarize or hyperpolarize if I open a particular gated ion channel. So if I open a sodium gated ion channel, I expect the sodium will come into the cell. That will bring more positive charge into the cell, and that will depolarize the membrane potential. If instead I open a chloride gated channel, I expect chloride to also move into the cell based on its concentration gradient, but it's bringing more negative charge, which is hyperpolarizing the membrane potential. So now that I have done sodium and chloride, let's see how well you understand this by trying out the same logic. But now we're going to open up a potassium gated channel. So if I open up a potassium gated channel, is my membrane potential going to depolarize or hyperpolarize? It's going to hyperpolarize. Now, why? The first thing we need to understand is that potassium will want to move out of the cell. We're simply giving potassium more opportunities to move out of the cell. And when potassium moves out of the cell, it takes that additional positive charge and moves it from the inside of the cell to the outside of the cell. So by shifting that positive charge to the outside of the cell, the inside of the cell relatively to the outside of the cell becomes more negative. And so it actually hyperpolarizes the membrane potential. So potassium exiting hyperpolarizes the membrane potential. What if I open up a gated calcium channel? Will it depolarize or hyperpolarize the membrane potential? It's going to depolarize the membrane potential, but probably not a lot. Why? Well, calcium is concentrated in the extracellular fluid relative to the intracellular fluid, and so we do expect that calcium will want to come into the cell, but there's not a lot of calcium to begin with in either compartment. So if I open up a calcium channel, there's just not going to be a lot of calcium around that's going to want to take advantage of that pathway, just because the millimolar concentration is so low to start with. So a little bit of calcium will trickle in, and it will depolarize the membrane, but you're not going to see a huge depolarization. You're going to see more of a gradual depolarization. All right, that's where we're going to stop on this lecture. And if you have a pretty solid understanding of depolarization and hyperpolarization and being able to predict which one is going to happen if I open a gated channel, then you are going to be well prepared for our next lecture where we start talking about action potentials. So I'll see you then.